Okay, now let's talk about some operations that we can do with these vectors. Let's suppose we've got a vector v and we've got a vector u. Okay, so we've got these two vectors and we want to add them. So we want to find out, well, what does it mean to add two vectors together? We know how to find the magnitude, we know how to put the vectors in component form, we know how to find the direction angle, but what about if we had two vectors and we want to add them? Okay, so we have these two vectors. Now, let's just think about something a minute, and because we're going to tackle two things at once here. I'm going to show you how to actually add the vectors and what it means geometrically. Now let's suppose that I just copy this vector u, and without changing its direction or magnitude, I just slide it up, its copy, so that the initial point of that vector starts at the terminal point of v. And then I do the same thing for v. I make a copy and slide it over here without changing its direction or magnitude, so that its initial point starts at the terminal point of u. Now notice this, they come together up here at this point 8, 6. See? There's 8 and 6. That's where these vectors come together. Now, let's actually add these vectors. So, I've got u plus v. Now when we see this, when we're told, okay, find u plus v, it means to add the corresponding components. So I'm going to add the 3 and the 5 together to get the x component of the addition vector, and then the 4 and the 2 to get the y component. And when I do that, notice I get this vector 8, 6, which corresponds to this point right here at the end of this parallelogram. See, it's like if we make a parallelogram, the addition vector is going to be the diagonal of that parallelogram. Okay, so this is how we add vectors, and this is the geometric interpretation of it. It's the diagonal through that parallelogram. Now, let's think about subtracting vectors. Let's think about v minus u. Well, we're going to do it the same way. V minus u, I'm going to take the 3 minus 5 and 4 minus 2. See? I get that vector. And when we do that, we get this vector over here. Whoops, we get, if you plot the point, negative 2, 2, that's this vector. So the terminal point is right over here at negative 2, 2. Now, that's how we do the subtraction of these vectors. But what is the geometric interpretation of that? Well, let me make a copy of that vector and slide it over this way. Now notice I haven't changed the direction or the magnitude. But what I've done is I've just slid this vector up and put its initial point on the terminal point of u and the terminal point on the terminal point of v. See? So notice v minus u, if you want to see a picture of what that looks like, it's a vector. Now notice I'm still writing the vector starting from the origin and going up to negative 2, 2, but it's parallel to this vector over here. So you could slide this vector up here, and what you have is a vector v minus u. It starts at u and goes to v like this. This is the way you could draw to represent that subtraction. Okay? Because those vectors have the same direction and magnitude. Now, let's talk about scalar multiplication. Let's suppose we've got a vector, this 3, 4. We've been working with this vector, and we want to multiply it by 6. Well, literally, that just means this. It means we take 3, 4, add it to 3, 4, add it to 3, 4, and so forth. And we know, we just learned how to add vectors. We add the corresponding components. So I had 3 plus 3 plus 3 plus 3 6 times, and the same with 4. Or another way to look at that is 6 times that vector 3, 4 is just 6 times 3, comma, 6 times 4. We just multiply each component part by 6. Now something interesting about that is, well, what does that do to the magnitude of the vector? Well, let's check out the magnitude. If we take the magnitude of that vector, we're going to get the square root of the first component squared plus the second component squared, the square root of that sum. And notice I could factor out a 6 squared because there's a 6 squared here and here, and then I take the square root of 6 squared and I just get 6. So it's just like I'm taking 6 times the magnitude of the vector. So if we have a vector and we multiply it by a scalar, what does that do to magnitude? Well, it's like multiplying the magnitude by that scalar. So 6 times v, the magnitude is going to be 6 times the magnitude of v. Now that leads us to an observation here. What if we want to find a vector that has only a magnitude of 1? In other words, we want a unit vector. Well, we already know that if I multiply a vector by some scalar, that scalar acts as a multiplier for the magnitude. Okay, so let's look at a unit vector. Let's suppose we've got this vector 3, 4, and I get the magnitude of it, which is 5. Now, that's the magnitude. What if I take that magnitude and say, okay, I'm going to divide that vector by its magnitude? Well, what does that do? Well, we would be, the magnitude is 5, we would be multiplying the magnitude by 1/5. Well, if the magnitude is 5, we would get this. And think about that. Let's check out this, see what the magnitude is. Okay, we would have 3/5 squared plus 4/5 squared. That's 25/25, which is 1. The square root of 25/25, which is 1. So we have this vector, and we divided it by its magnitude, and what we get is another vector down here that has the same direction, only its magnitude is 1. This vector's magnitude is 5. This vector down here, this is a unit vector.